Okay, good morning. Welcome to Introduction to Photonics. In our last lecture, we were talking about avalanche photodiodes, and we got to the point of saying that when you are looking at the avalanche photodiodes, the multiplication factor is a function of the bias voltage. So, larger the bias voltage, more will be the multiplication factor. But we were insisting that what matters is not just that number, but the quality of that multiplication factor, meaning whether that multiplication factor is achieved without accumulating noise, right. And so, we had to look at that picture on the right side, where we said okay, the noise is actually given by this excess noise factor, and if you look at the excess noise factor, you are saying that when k equals to 1, which corresponds to the ionization coefficient of electrons is equal to the ionization coefficient of holes. In that case, even as you accumulate gain, you are also accumulating noise. So, overall we are not really gaining much, we are not gaining in terms of the signal to noise ratio. Whereas, if you say k equal to 0.1, up to a certain multiplicative gain, there is not as much increase in the noise, and so there may be some optimum operating point for these APDs, right. So, we considered that, and then we said okay, we looked at some sample numbers for silicon and indium gallium arsenide sort of APDs, and then we said okay, since we started talking about signal to noise ratio, we want to look at what is noise, mean in a photodiode, and it's in a typical case, it's not just the photodiode that matters, you need to extract the current in the external circuit. So, you have to look at it overall as a photoreceiver. So, when we look at the receiver noise overall, we are basically saying there will be one component which is the short noise, and the other component is the thermal noise. A short noise is due to the random arrival of photons and the subsequent electron hole pair generation, and we quantify that the short noise variance is proportional to the photocurrent, and then also the bandwidth of your receiver, and similarly you have the thermal noise, which is given by this expression, which is due to the fact that the electron flow inside the current flow inside resistor tends to be random in nature, and that actually depends on the value of the resistor. Now, we will go further on this. The primary thing that we want to establish is when does it make sense to use an APD, and when are you better off just using a PIN photodiode. Okay. Can we actually define the regimes over which APD makes a little more sense. Okay. So, let us go into that a little more detail, and when we talk about short noise, okay, we defined it as sigma I square is equal to 2 times, I said E, but your book is actually insisting Q. So, let me just switch over to Q, but you understand the Q is just representing the charge of an electron. So, 2Q multiplied by IP, but also there is one more component that you typically have, a noise component that you typically have, and that component is called the dark current, okay, multiplied by B. So, what is the dark current? when we talk about these biased photodiodes, we are typically talking about this barrier height. This is in terms of energy. So, the barrier height is V naught plus V b, where V b corresponds to a reverse bias, right. So, the barrier height keeps on increasing with higher reverse bias, and in this sort of a scenario, even at room temperature, you might have an electron jumping from the valence band to the conduction band, and so this is a case where there is no photon going in, right. So, it is dark, right. There is no photon that is incident on the photodiode, but nevertheless you have thermally excited carriers which jump the band gap, and they become like a free electron. Okay. And that process actually depends on the barrier height, because as you can see, with larger and larger barrier height, with a little bit of vibrational energy itself, some phonon energy, you can tunnel across. That electron from the valence band can tunnel across and get to the conduction band. Okay. So, you have more dark current happening at higher bias voltages. Okay. But even at even when you do not apply a bias voltage, there is a finite probability that an electron can jump over to the conduction band, which is called a thermally generated carrier, and that can also give you a photocurrent in the external circuit. So, which is what we are calling as the dark current. Okay. So, you have this sort of an expression for your PIN photodiode, and when it comes to an APD photodiode, your total noise is going to be something like this. There is a factor m square multiplied by f that comes about in an APD. Once again, I am not deriving that formula. It's a fairly long derivation, but you have that sort of an expression where f is given by, like I mentioned in one of the previous lectures, it's k multiplied by m plus 1 minus k multiplied by 2 minus 1 over m. Okay, that's actually called the excess noise factor. Okay. So, we have short noise and we have thermal noise now, which is 4 kBT over RL multiplied by B. So, when you look at the overall signal to noise ratio, signal to noise ratio is defined as your signal power over the noise power. The signal power is going to be given by this IP square, and your noise power is given by now it has two components, sigma x square plus sigma t square. That is the short noise variance and then the thermal noise variance, right. And if you write this out, you can basically say that the photocurrent is going to be given by you have a multiplicative gain as far as in a general case in an APD, eta multiplied by q, that is the responsivity, eta q divided by h nu is the responsivity multiplied by the incident power, right. But the incident power over h nu is nothing but the photon flux. So, I can just write this as m into eta q multiplied by the photon flux, right. Flux is representative of the incident power divided by the photon energy. Okay. So, this the whole square divided by your it is 2 q multiplied by I p. Let us actually neglect I d, because I d tends to be relatively small number. So, we will neglect that for a minute. So, for simplicity, and then you have 2 q multiplied by once again I p, which is corresponding to that term in the numerator. So, there is actually a q that comes from there. So, you can write as a 2 q square m square f eta phi multiplied by b, right, where m square f actually corresponds to the noise, the extra factor that comes about when you use an APD, plus you have your sigma t square. Okay. You can further simplify this, right, and you can actually try to get to the point where when you have very few photons falling on the detector, right. So, you have what is called the short noise limit, which corresponds to very few photons actually that would be very few photons falling on the detector will be the will be what is called the thermal noise limit, because there is no short noise. You understand that short noise comes about when we have a light more light falling on the detector, but when there are very few photons falling on the detector, then you have what is called the thermal noise limit. So, in this case what you have is sigma s square is far less than sigma t square. M is actually the multiplicative gain.
Sigma s square m q, because 2q m square f is the factor.
So yes, so you yeah, I p will have m cube, that is right. So yeah, we are neglecting dark current, yeah. So let us see if we can erase this. Yeah, thanks for pointing out. So, this should be m cube here, there is a extra m that comes about through I p. Okay. So, we can just say that when you have the thermal noise limit, that is sigma t square is far greater than this other factor, then you know that your short noise is so low that you can afford to use an APD and increase the short noise. So, in my thermal noise limit, when you have very few photons falling on the detector, my thermal noise is over here. My thermal noise depends on the receiver gain that I will set up, right. So, more the gain, more will be my thermal noise. Okay. So, my thermal noise will be over here, but my short noise is over here. Okay. Now, if I use my APD, I can afford to go up on my short noise without affecting the overall noise that is accumulated, right, because this is so low initially. Now, if I use an APD and increase my gain, my short noise is going to increase, okay, but until it reaches thermal noise, it is actually not affecting the denominator. Until it becomes comparable to the thermal noise, it is not affecting the denominator. So, but it is affecting the numerator, right, because your gain is actually that multiplicative gain is contributing to the numerator. Okay. So, the overall signal to noise ratio is going to increase. Do you understand that? When you have very few photons falling on the detector, so that your short noise is very small compared to the thermal noise, in that sort of a scenario, you can afford to increase your short noise. You can afford to increase your short noise by going to a multiplicative gain, which actually boosts up the numerator by quite a bit, by that square factor m square, right. And now, because of that, you are able to increase your signal to noise ratio with that multiplication factor. Do you have any questions on that? Do you understand what I am saying? Yes. So, when it becomes equal, then you have twice that noise variance, then it becomes significant. So, but just before it becomes equal, that is all controlled by your gain, right. Your multiplication factor controls, you have only few photons falling. So, you are not going to be able to do anything that, but you can control how many electron hole pairs you are generating with that through that multiplicative gain. Yes. So, with the APD, we are by changing the bias voltage, we are controlling the m factor, that multiplicating gain factor. So, through that you can actually control the signal to noise ratio. So, initially as you increase, you just get a free improvement in the signal to noise ratio, so to say, right. It does not have a penalty until the short noise becomes comparable to the thermal noise. So, intuitively you can say, when you have very few photons falling on your detector, such that the short noise is much lower than the thermal noise, which we call as the thermal noise limit, right. If you have a thermal noise limited receiver, it actually makes a very good case for using an APD. Okay. But beyond that, in the short noise limit is where the first factor in the denominator is larger than the second factor. Then in that case, what happens? It basically is like you have a 1 over m dependence, right. You have a 1 over m dependence. So, in that case, you are, as you increase your gain, you are actually lowering the signal to noise ratio, right. The short noise limit, you have a m square factor in the numerator, you have a m cube factor in the denominator. So, it overall becomes a signal to noise ratio becomes inversely proportional to m, and in that case, increasing the m is only going to reduce the signal to noise ratio. Okay. So, let us actually try to put all of this together in some meaningful form. So, to do that, let us actually say you have you can count the number of photoelectrons. That is a mean number of photoelectrons. Mean number of photoelectrons is given by eta multiplied by phi, which is what we have in the previous case, divided by 2b, where 2b corresponds to the well, 2 times the bandwidth of your photoreceiver. Okay. So, the number of photoelectrons will be given by this. So, if you substitute this in that previous expression, what you get is SNR is now going to be given by you have an m square in the numerator, and then you have that factor eta phi and you have a 2b factor in the denominator. So, you are going to have m square multiplied by the mean photoelectron square divided by m square f multiplied by the mean photoelectron plus some sigma q square. Sigma q square is nothing, is going to be nothing but sigma t square divided by 2b, right. There is going to be some normalization factor, but sigma q square is a representation of the thermal noise. But what we have done here is we have represented the entire thing in terms of number of photoelectrons. So, that can actually give us a more insight into this entire scenario. So, you have SNR plotted as a function of the number of photoelectrons, and in this what you will find is without APD you are going to have something like this. You are going to have your SNR increase with mean number of photoelectrons, and and so more the photoelectrons, more will be your SNR. But if you can, so this is without APD, but with the APD what you will find is it goes something like this. So, when you have low number of photoelectrons, it helps to use an APD, but beyond a certain point, right, the APD is going to actually give more noise. If you keep increasing your if you have a large number of photoelectrons falling on your APD, that short noise component is going to dominate, and when that short noise component dominates, then you essentially have lower signal to noise ratio. Okay. So, this sort of a picture determines when you use the APD. You use the APD typically in these regions where you have very few photoelectrons falling on the photodiode. So, this is the number of photoelectrons, that is right, that should be m cube. So, that is that should be m cube over there, because we are just counting in terms of number of photoelectrons. So, the other question, what is sigma q square? Sigma q square, there is actually a normalization factor, because we have taken 2b in the numerator. There is actually a normalization factor that corresponding to that 2b that comes into that. So, sigma q square is actually sigma t square multiplied by 2b, I think. I am not absolutely sure, but it is actually sigma t square multiplied by 2b is what it will come. If you just substitute instead of eta phi eta phi you substitute basically that factor m bar, then you will get this. Okay, but the primary idea is that you can look at it in terms of photoelectrons, or you can go one step before this and say I want to look at it in terms of the number of photons that are falling on the photodiode, right. So, that will be a very similar picture that you see here. So, when you have very few photons falling on the detector, then you use an APD, but if you have a large number of photons falling on your detector, then you are better off just using a PIN photodiode. Okay. Now, of course, then you would say I can then use an APD in all my applications and just change the bias voltage, right, because if I keep my bias voltage low, it acts like a PIN photodiode. So, I can actually determine where I operate, right. That is one thing that you can do, but for the fact that an APD is more expensive than a PIN. So, in applications where you are going to have a lot of photons that are going to fall on your photodiode, like in certain sensor applications, you may actually have a lot of photons falling on your photodiode, then in that case you are better off with just the PIN photodiode. But on the other hand, let us say in a communication type of application where you are going long distance and you have to when you have very few photons remaining after it is gone through all that distance, then you may want to put an APD there, because that is going to give you a better signal to noise ratio. Okay. So, you just need to see what is the relative components of your short noise and thermal noise, and based on that you decide whether you want to use APD or PIN. So, any other questions about this before we move on? So far we have been talking about what is happening to the photodiode. We have not actually figured out what is happening in the external circuit. Okay. So, the question is how to extract the photocurrent efficiently, right. So, we have been saying okay, yeah, these electron hole pairs are generated, they are swept out into the external circuit and they are going to generate that photocurrent, and we said okay, life is nice and dandy, right. So, there is nothing to worry about, but in reality you do have to worry about, because let us say you take this simple example of a photodiode which is reverse bias, means that the cathode is connected to a positive bias, let us say, and let us say you are just trying to extract the output through just a load resistor RL, right. So, you just take V out like this. So, what is the problem with this? Now, the problem is that you have a photocurrent that is flowing through this resistor, and when that photocurrent flows through, this is going to be at higher bias compared to this, right. You are going to have a potential drop across that resistor RL. So, when photocurrent flows through this RL, it is going to have a potential drop corresponding to IP multiplied by RL, okay, and that voltage drop, if you look at it, is acting against this VB, because VB here is positive, right. Now, if this potential is actually acting on this anode side, that is actually like forward biasing. So, through VB we are trying to reverse bias the photodiode, but because of as you extract more and more photocurrent, there is a voltage drop across the RL that actually is forward biasing the photodiode. So, it is counteracting the reverse bias, in other words, right. So, that is actually going to be a problem, because if it is counteracting the reverse bias, then the reverse bias voltage, effective reverse bias voltage that the photodiode is seeing is going to keep decreasing as you go to higher and higher photocurrents, as you pick up more and more light. Okay. So, let us just represent this through the what we are previously looking at as your IV characteristics, right. And what we said previously is the IV characteristics are like this, and as you increase your the light that is falling on the photodiode, you are going to have a corresponding increase in your in the photocurrent, right. So, this is basically with respect to increasing intensity of light falling on the photodiode. Okay. But because of this, what we are saying is we are starting with some reverse bias over here, but as you increase the intensity, the photocurrent gets increases, photocurrent is increased, and that is actually reducing the effective bias across the photodiode. So, my load line, the so called load line is going to be like this. This is called what is called the load line. As I am loading the photodiode, right, the corresponding current that I am going to have is actually going to be limited by this load line, because effectively my reverse bias, which I started with this, right, this value VB, that reverse bias is getting compromised as you go to higher and higher intensity of light falling on the photodiode, as you extract higher photocurrent. Okay. So, my load line is like this. Ideally, you want a load line that looks, that is straight, it is vertical. What it means is that even as I increase the photocurrent, I am not changing the reverse bias, affecting the reverse bias. So, how can you achieve that? The way you can achieve that, I am running out of time. So, I will just quickly mention this and I will stop here, is by going for an op-amp based circuit. So, you typically connect the negative of the op-amp and the positive terminal is at virtual ground, and then you have a feedback resistor RF over here. Okay. So, this one is called a transimpedance amplifier, because the output is given by RF multiplied by IP. It's converting a photocurrent generated due to light falling on the detector, just the same way this is, right. It is converting the photocurrent to an output voltage. So, that's why it is called a trans impedance amplifier. In short, it is called TIA. Okay. In this case, what is different? What is different is you are trying to push a photocurrent into this op-amp. The op-amp, an ideal op-amp would not allow any photocurrent, any current to flow into the terminals, right, and it will always try to keep the potential at both these points, potential difference to be 0. How does it keep the potential difference to be 0? It basically generates a current, it sources current at the output, which actually flows through this, and then it negates that potential that you have over here, right. So, that is how you see this V out as minus RF into IP. So, irrespective of whatever current it generates, right, as long as this op amp has the capability to negate that, op amp is able to source a current to negate that, you are going to be fine. If you have come into a condition where you are generating much more photocurrent than what the op amp can supply, then you are in trouble. But that usually does not happen, because the photocurrents that you generate are in the order of milliamps, and the op amps can easily provide tens of milliamps. Okay. So, in this sort of a case, you do not have a loading like this. Instead, your load line will be like this, or if you keep a bias, it will be like this. It will be just a vertical line. Okay. So, you are not compromising your bias while you are extracting more photocurrent. So, in most of these conventional applications, you use a transimpedance amplifier as the way of extracting photocurrent and converting it to a external this thing. There are some very special cases when you want to have very high bandwidth, very good response. In an op amp based circuit, you are always going to be limited by what is called the gain bandwidth of your op amp, meaning the bandwidth that the op amp that can provide for even say unity gain is going to be limited. So, beyond that bandwidth you cannot use that op amp, right, for this purpose. Whereas, in those sort of cases you can use the what is called the direct loaded configuration, and so you would see that high speed circuits where you want to have gigahertz type of bandwidth, you use a direct loaded configuration, whereas relatively lower speed circuits you go for a transimpedance amplifier.